we're going to start our problem with a rectangle. Then, using the base of this rectangle as a hypotenuse, we will construct a right-angled triangle inside our rectangle. And in this way, we will divide our rectangle into 3 triangles. Now, let's inscribe 3 circles inside our 3 triangles. And let's say that the circle on the left has the area of 2, the one on the right has the area of 3, and the question is, what is the area of the circle in the middle? This awesome question was sent to me by my subscriber Z, and thank you so much for the wonderful suggestion. Now you guys can pause the video, as always, try it out for yourself, and then come back and check the solution. Alright, so let's solve this problem together. First, I'm going to label all the vertices of our rectangle as A, B, C, and D, and I will label the apex of our inscribed right-angle triangle as E. Now, let's have a look at the inscribed circle on the left first. We know that the area of any circle equals pi times the radius squared, and we're going to use this fact for the first circle. And while we are here, let's label the radius of this green circle as R1. Now we're going to do the same thing for the blue circle on the right. We can say that the area of this circle equals 3, and we can say that the radius of this circle is R2. Finally, let's label the radius of our wanted red circle as R, and then we can say that the area of this circle must be pi r squared. Alright, so now let's simplify our image and let's focus on the inscribed right-angled triangle ABE. Let's label the hypotenuse of this triangle as x and the acute angle at the point B as theta. Now, let's do a little bit of trigonometry. First, we can say that the cosine of the angle theta is nothing but the relation between the leg EB and the hypotenuse AB. From here, we will get that EB is AB times cosine theta, and if we substitute the value of AB for x, we will get that EB must be equal to x times cosine theta. Now, correspondingly, we can do the same for sine theta, but this time the sine will be equal to the other leg EA over the hypotenuse AB. So we can write this down in terms of EA, and if we substitute the value of x for AB, we will get that the other leg EA must have the length of x times sine theta. And let's implement those values into our sketch. Now, let's clear this image and take a look what we have. Those legs EA and EB are not just the legs of our inner triangle, but they also represent the hypotenuse of our 2 smaller triangles on the left and on the right. And if we somehow can prove that those 3 triangles are similar, maybe we could do something with those values. So let's try to do that. First, let's take a look at the red triangle AEB and the blue triangle ECB. Now let's use a really interesting theorem, which is called the angles in parallel lines. This theorem states that if we have 2 parallel lines and we pull a line through them, which is called a transversal, then the alternate angles must be identical. As you can see, this is exactly the case on our sketch on the left, because the lines AB and EC are parallel lines and the line EB is a transversal. This means that the acute angle at the point B, which is theta, must be identical to the acute angle at the point E, since those 2 angles are alternate angles. Now, have a look at the overall angle at the point E. This angle is a 180-degree angle, and it consists out of 3 smaller angles: the acute angle theta on the right angle in the middle, and this other acute angle on the left. Now, since all three angles must be 180 degrees and the angle at the middle is a 90-degree angle, this means that the sum of the two remaining acute angles on the left and the right must be 90 degrees. So, the angle DEA must have the value of 90 degrees minus theta. Now let's take a look at the right-angled triangle DEA, this green triangle. Since it is the right-angled triangle, this means that the sum of the two acute angles of this triangle must be 90 degrees. Since one is 90 degree minus theta, the other one at the point A must have the value of theta as well. Now we have this interesting fact. Because all three triangles are right-angled triangles and all three of them share the same acute angle, this means that those three triangles are in fact similar triangles. Now we're going to use this fact, but first let me give you a quick reminder about similar triangles. If we have two similar, let's say right-angled triangles, then the relation between their sides must be identical, and it is also equal to the relation between their in radii. Now, this last part, that the relation between their hypotenuse is equal to the relation between their in radii, is super important for us, and we're going to use it on our triangles on the left. First, let's do this for our big red triangle and our blue triangle on the right. We can say that the relation between their radii is equal to the relation between their hypotenuse. Then we will substitute the value of their hypotenuse, we will cancel out x and get that the relation between their radii must be cosine theta. Now let's do the same thing for the red triangle on the middle and the green one on the left. We can say that the relation between their radii equals to the relation between their hypotenuse, substitute the value of their hypotenuse, cancel out x, and get that this relation must be equal to sine theta. Now, what are we going to do with those two equations? Because we do not know the value of theta. Well, we're going to do something really interesting. We're going to put those two equations to square. Why are we doing this? Well, you're going to see the answer in just a few seconds. So, if we do this, we will get the following two equations. And now, we're going to add those two equations and get this following big equation. Now, let's remind ourselves about one really awesome trigonometry relation, which states that the squared sine of any angle plus the squared cosine of the same angle must be equal to 1. And if you take a look at the right side of our newly formed equation, this is exactly our case. So this means that the right side of our equation must have the value of 1. Now, we're just going to multiply this by r squared. We can do this safely because we know that r cannot have the value of 0, and we will get the following. And finally, we're going to multiply our new equation by pi. And if we do this, we will get this final equation. Now, if you take a closer look what we have here, you can notice that those terms inside our equation are nothing but the areas of our three inscribed circles. So, the area of the green circle plus the area of the blue circle must be equal to the area of the red circle. And let's write this down in this way so it is a little bit more natural. Now we can just substitute the values of the areas of those two circles, and we will get that the area of the red circle in the middle must be equal to 5 squared units, and this is our solution. Well, I really hope you guys enjoyed this interesting problem. If you did, do not hesitate to leave a like or subscribe to the channel for more content like this. Of course, if you found another way to solve this problem, please write it down in the comment section. And until next time, see you guys and take care.